Aduh, I want to see the moon but I cannot see anything. Wow, people thought we need this binoculars so I can see something far from me.
NANI?!
But it's so ridiculous, expensive, right? Oh no, how ah? Ish, I cannot see anything, even the moon. Oh no. Oi! Hey! Who are you? Huh?
Relax, my friend. Relax. Okay, I'm here to help you.
Okay.
I walk by, I see from afar that you are trying to see the moon.
Yes, because using binoculars, people say I can see anything far from us, even the moon.
Oh, I think you are misunderstood, my friend.
Misunderstood?
It's not binoculars, but it's actually a telescope.
Telescope?
Yeah, lucky for you, I brought my telescope today.
Oh wow! Wow, telescope. So it's not good. Okay, I can go away.
Yeah, right. I bet you can see the moon right now.
How can I see it? How you use it? Oh my God, that's.
Hey everyone, did you guys see my latest sketch just now? Okay, my name is Hazan Iman, and I'll explain to you all about a marvelous invention called reflecting telescope. Do you want to know more? Let's go! There are many kinds of telescope in this world, such as the reflecting telescope and the Schmidt-Cassegrain telescope. But what I am interested to share with you guys is the reflecting telescope. But before that, what is a telescope? Okay, telescope is a tool that astronomers use to see faraway objects. Most telescopes and all large telescopes work by using curved mirrors. It uses to gather and focus light from the night sky. The reflecting telescope was first invented by Isaac Newton in the 17th century. At that time, it uses spherical ground metal as a primary mirror and a small diagonal mirror in an optical configuration. The late 20th century has seen the development of adaptive optics, and reflecting telescope was ubiquitous on space telescope and many kinds of imaging devices. First, we have the eyepiece lens that is used to bring light from the primary mirror that has been focused. Once the light reaches the eyepiece, it magnifies the image so that we can see the image clearly. It has the same principle in the magnifying glass. Next is the primary mirror. It is located at the lower end of the telescope tube in a reflector and has its front surface coated with an extremely thin film of metal such as aluminium. The primary mirror usually has a concave spherical or parabolic shape, and as it reflects the light, it inverts the image at the focal plane. Last but not least is the secondary mirror, which is a convex mirror. The secondary mirror concentrates the light into a beam that travels back through a hole in the primary mirror, where the eyepiece is located. Unlike a lens, a mirror can be very thin. A bigger mirror does not also have to be thicker. Light is concentrated by bouncing off the mirror, so the mirror just has half the right curve shape. It is much easier to make a large near-perfect mirror than to make a large near-perfect lens. Also, mirrors have their own problems. Have you ever looked into a spoon and noticed your reflection is upside down? The curved mirror in a telescope is like a spoon. It flips the image. Luckily, the solution is simple. We just use other mirrors to flip it back. There are two general properties to determine how good is the telescope. The first is how well it can collect light. The diameter of a mirror and lens plays an important role because when the aperture is bigger, more light can be received, which means more brighter and clearer image will be formed. Next is how much it can magnify the image. It actually depends on the combination of lens, but remember, the eyepiece will do the magnification, not the lens. Light rays change direction when they reflect off a surface, move from one transparent medium into another, or travel through a medium whose composition is continuously changing. The law of reflection states that on reflection from a smooth surface, the angle of the reflected ray is equal to the angle of the incident ray. The reflected ray is always in the plane defined by the incident ray and the normal to the surface. The law of reflection can be used to understand the image produced by plane and curved mirrors. Unlike mirrors, most natural surfaces are rough on the scale of the wavelength of light, and as a consequence, parallel incident light rays are reflected in many different directions. Diffuse reflection is responsible for the ability to see most illuminated surface from any position. Rays reach the eyes after reflecting off every position of the surface. In a reflecting telescope, light rays from distant objects, which are essentially parallel, strike the concave mirror at the same angle. The rays are then reflected back up through the telescope tube towards the focal point. However, before they reach the focal point, they strike a secondary flat mirror that is tilted at a 45-degree angle. The secondary mirror diverts the light out through a hole in the side of the tube. The eyepiece lens then focuses the light. This produces a magnified image. Also, the image appears much brighter than it does to the naked eye, because the mirror gathers and concentrates the light. The shape of the spherical mirror affects the image that is reflected. Light striking near the edge of the mirror does not focus at the exact same spot as light striking nearer to the center. This results in what is called spherical aberration. This phenomenon is often corrected by using a combination of lens, or in the case of large telescopes, by using parabolic mirrors, which are shaped like rounded cones that focus all the light from a source to a single point. There are several disadvantages and limitations of the reflecting telescope. First one is the maintenance. Because of their size and the design of an open tube assembly, the mirror must be cleaned periodically. Whenever it is cleaned, it also must be realigned, which can be expensive. An improperly aligned telescope results in a blurry image. The next disadvantage is the surface. The single reflective surface in a telescope's mirror allows it to be large, but it is also exposed to the air. Originally, reflecting telescopes used mirrors coated with silver surface, which tarnish in the open air. These telescopes require regular polishing to keep them clear. Now, reflecting telescopes' mirrors are coated with aluminium, which also oxidize, but the product is clear and does not require as much polishing. Even with modern telescopes, the metal coating of the reflective surface needs to be replaced after years of service. Here's a little recap about what we have learned today. First, we know about the function of each part of the reflecting telescope. It consists of the primary mirror, the secondary mirror, and the eyepiece. All are important in making the telescope work. Next, we also learn about why we use mirror. It is much easier to use mirror and easier to take care of it. Moreover, it costs less troublesome. Other than that, we also learn about the general properties. We know that if we have bigger mirror means bigger aperture, which means more light can come through, and it will produce more clearer image. We also learn that we use lens to magnify the image, not the mirror. We also learn about how the law of reflection evolved and applied in this instrument. But not least, the limitation of reflecting telescope. Reflecting telescope need high maintenance. If it's not maintained properly, it will cause the image to be blurry. Then the surface is sensitive. It needs regular polishing.